Yes, good evening. So, um, today looks like we don't have any audience here, but anyway, when you see this video, you can learn. And if you have any doubts while I solve this problem, you can always share your questions in the discussion forum. Okay. So today, what we will do is we will be solving three more problems, okay, related to thermodynamic property relations. Some of it we already did in the last week. This week we will be emphasizing on some more topics like Joule-Thomson coefficient and uh, you know the internal energy function that we learned, internal energy equations, two internal energy equations, and also something related to Clapeyron equation. Okay, so I have three questions today. We will go forward, and if you have any doubts, you can always share your doubts in the discussion forum. With that, let's start. Let's quickly go through the first question. The first question tells there is a 1 mole of argon at 400 Kelvin is initially confined to one side of a rigid insulated container. Okay, so we have a rigid insulated container and there is 1 mole of argon at 400 Kelvin, and it is also confined at one side of the rigid container, which is divided into two equal volumes of 0.3 meter cube by partition. Okay, so let's quickly draw that container. So it might look something like this. Maybe I will use black color. Yeah, so this might look something like this, and then we have a partition, right? And initially we had 1 mole of argon. Let's write it. Sorry, 1 kilomole of argon. 1 kilomole of argon. Okay, and the temperature is 400 Kelvin, and the volume is zero point 0.3 meter cube. Okay, and it is also insulated container. So let's draw something like this. So there is no heat interactions, especially, right? And here also it's zero point 0.3 meter cube. It is divided into two equal halves, right? So that is what given. The other side is initially evacuated, so it is empty, there is nothing here. Okay, the partition is removed and the argon expands to fill the entire container. Now this partition is removed. Let me just draw that container too. Maybe I will just copy paste this. But here the partition is removed, that's it. So it goes from this state to this state. Now the same 1 mole of argon, but the total volume is zero point 0.6 meter cube, right? Okay, and what else is given? And using the van der Waals equation of state determined its final temperature of argon. So we were asked to use van der Waals equation of state. Okay, so the argon gas is actually modeled using van der Waals equation of state, and we should find the final temperature of argon. So basically we need to find T here. Let's call this 1 and let's call this 2. Okay, so then this becomes T1 and this becomes T2. So we need to find what is this T2, and what is given is we can find we should use van der Waals equation of state. Then repeat it using the ideal gas equation of state. So we were asked two different ways. One is when the gas behaves as a van der Waals equation of state, and one when gas behaves as an ideal gas, right? So let's first try the first one. using van der Waals equation of state. But before going that, let's also understand few more things. Since it's an insulated container, basically there is no heat interactions. So there is no Q out or Q in, right? Which is equal to 0. And since this is also uh, maybe let me not put it here, let me just write it down here. So since it's a insulated, Q interaction is 0, Q is equal to 0, and it is a rigid container, so the work done is also 0. Okay, so since Q and W is 0, we know from the first law of thermodynamics. So the first law of thermodynamics states the change in energy, here we will write it in terms of internal energy, okay, because other things we are ignoring, and it is also other kinetic energy and potential energy is not going to change for this. So change in energy is Q minus W, which is going to be equal to simply 0. So from first law, del U is equal to 0. So this is going to be U2 is equal to U2 minus U1 is equal to 0, which is U1 is equal to U2. Okay, so this is just additional thing. Important thing is the change in internal energy is 0 for this during this process. Now let's we should find final temperature. Okay, let's see how we can find it. We don't know what kind of process is this, right? So first let's use van der Waals equation of state. I think there will be double A, van der Waals equation of state. So how does van der Waals equation of state looks? It will be something like pressure is equal to RT by V minus B minus I think A by B square. So B and A here are constants. Let me just write that down also. A is going to be 27 by 64 R square TC square divided by PC. Okay. All right. Now, how do we find the final temperature? Basically, right. So what we know is we know del U is equal to 0. The change in internal energy is 0. So what and it is also a rigid insulated container, which means you can write this as you can write internal energy as a function of T and V, right? So let's find the total. We can how do we say? Let's find the exact differential of internal energy, which is or the total differential of internal energy or the total change in internal energy, which is du. You can write it like so: dou u by dou t at constant v dt plus dou u by dou v at constant t dv, right? Now what do we know here? We know that dou u by dou t at constant v is going to be our cv, right? This is nothing but our cv. So let me rewrite this then. It can be written as du is equal to cv dt plus dou u by dou v at constant t dv. And now you can recall the first internal energy equation which we discussed in the which professor discussed in the lecture. So if you look at it, there will be one equation called maybe I will write it like this: recall dou u by dou v at constant t is going to be t times dou p by dou t at constant V minus P. Alright, so this is the expression we get from the uh, internal energy equation. Let me just quickly go through that also. So what we have here is so this is the equation, right? um, yeah, these are the two internal energy equation. I'm using the first one. Let me just write it here also. Right, so this is the first internal energy equation. Now let's substitute this also over there. So if you substitute it back, let me call this substituting 1. What happens, the total change in internal energy is going to be Cv times dt plus T times dou P by dou T at constant V minus P times dV. Alright, now what do we know? We know that du is equal to 0, right? So we can write this as equal to 0. So now let's apply this van der Waals equation of state and try to find out this term. Okay, this dou P by dou T at constant V, because we know the equation of state. Let's use that. We know P is equal to, what is RT by V minus V, RT by V minus V minus A by V square, right? Now what do we need to find out? We need to find out dou P by dou T at constant V. So let's say if you differentiate it at constant volume, we are going to retain only this term. This term will go to 0 because uh, this doesn't depend on temperature, right? It's just volume. So this is going to become R by V minus B, right? So B is a constant, V is also constant in this differentiation. R is also constant, so only differentiation is with respect to T. So it's going to be simply R divided by V minus B. Okay, let's substitute it there. So we can write du equal to Cv dt plus, so T times R by V minus V minus P times dV is equal to 0. So let's substitute this also over here. What happens? Cv dt plus RT by V minus P minus P is going to be again RT by V minus B minus A by V square times dV is equal to 0, right? Now we can cancel these two terms. So this will simplify as Cv dt plus A by V square dV is equal to 0. Alright, now what do we need to find is we need to, so we know dV is going to be from 0.3 it went to 0.6, right? Initially it was only in the one half and suddenly it expanded to the entire volume. So we know dV. So what do we do is we will rearrange this equation. Cv dt is equal to minus A by V square dV. Okay. Now we can just integrate this, right? Let's integrate. if we integrate this from 1 to 2, we can also integrate this from 1 to 2. Now we need to know what is CV for argon gas, right? And also we need to know, we know that A is a constant, so let's take that outside. So minus A integral of 1 to 2 dV by V square. So 1 by V square is going to become V minus 2 plus 1 by minus 2 plus 1. So it's going to be minus into minus, plus will be the into 1 divided by V 1 to 2. So this can be written as A divided by V2 minus 1 by V1. Okay. Now, so let's write this down. It is going to be integral of Cv dt is equal to A times 1 divided by V2 minus V1. Okay. Now, what do we know about Cv? We don't know anything about Cv. There is a possibility. So from 1 to 2, what is changing is V is also changing and temperature is also changing. Now just take CV to be constant, and we can't just take it outside. We need to understand whether CV is a function of whether it is a function of volume, or whether it's a function of temperature, or it is a function of both volume and temperature. That we don't know. We need to find that out. So let's use another relation. There is the exact differential of entropy, right? So this is to know some information about CV. Because since we don't know what is the exact form of CV, how can we substitute? See, if CV is a function of temperature, we need to substitute some function over that integral, and then only we can integrate it, right? So we need to know about CV. So that is what we are going to do. We need to find whether CV is a function of V or T. Okay. Let's use one more uh, equation, which is the total differential of entropy, right? So I think this also you can take it from here. Yeah, this equation. So this equation, the change in entropy equation, right? So let's say if you use that, sorry, CV by T, it's CV, right? Okay, this is in terms of P. There will be one more equation. This equation. This equation is in terms of CV. Okay, so let's write that down. CV times dt plus dou P by dou T at constant V dV. Okay, now, okay, the same equation. Now we know that this is an exact, what do you call, exact differential, right? So this should be exact differential. So we use this exactness condition. So if we use that exactness condition, we can get some idea about CV. Okay, the exactness condition if we use. So what does exactness condition says? This is in terms of m dx plus n dy, right? So if that is the case, then dou m by dou y should be equal to dou n by dou x. This is what we know, right? Uh, if that is the case, here m is cv by t. So let's write dou by dou y is actually v times cv by t is nothing but this should be equal to dou by dou t, right? And n is dou p by dou t at constant v. So here also it is at constant x, and it's a partial, so anyway it's going to be at constant x and constant y. So this is also at constant v and constant t. Let's try to understand. So let's use this relation. Let me just simply rearrange this. You won't get confused. Right. So what do we know? We from equation of state we can find dou p by dou t. Dou p by dou t at constant v is equal to, I think we already found dou p by dou t at constant v, which is r by v minus v. Right. So let's use this r by v minus p. Now what we are trying to do is we are trying to differentiate this with respect to t. Here if you look at it, everything is a constant. Again we are going to differentiate with respect to t at constant volume, right? So this whole term is going to become 0. Let me just dou by dou t of by v minus b, right? So at constant volume, right? Again, so the, since it's at constant volume, this term is simply going to become 0. So if that is the case, then what this gives is dou by dou v of Cv by T at constant temperature is going to be simply 0, which means Cv by T is equal to some constant. It's not a function of temperature. It's not a function of volume, right? So this tells that Cv is only a function of temperature, not the function of volume. So it is not a function of volume. Okay, Cv is a function of only temperature. Let me just write it down here. Cv is only function of temperature. Now, one thing is clear. So Cv is going to be a function of temperature. So if we know that function, we can just simply put it there. Okay, that is there. Uh, what we also know is we know about argon. Argon is a monatomic gas. So Cv for argon is already known, which is nothing but 3 by 2 R. Right? If that is the case, we can consider Cv as a constant, and if we substitute it here, integral of 1 to 2 Cv dt is equal to A times 1 divided by V2 minus 1 divided by V1. Now if we substitute it here, we can write 3 by 2 times R integral of 1 to 2 dt. V2 minus 1 divided by V1. Okay. Let me write this also explicitly, not a function of volume. So now this is easy to integrate, and so it's going to be just T2 minus T1, which is going to be A times 1 divided by V2 minus 1 divided by V1. So we know a lot of things, right? So we know V2. V2 is going to be 0.06 meter cube, and V1 is going to be 0.03 meter cube. This is also known, and T1 is also given, which is 400 Kelvin, which is also known, I guess. Yeah, 400 Kelvin. Now we also need to find so these are specific volumes, right? So it should be meter cube per kilomole. So if you know, we used 1 mole of argon, right? So 1 kilomole of argon is in the entire container. So the specific volume of that gas is going to be total contain volume of the container divided by total number of moles of the argon present inside. So it's going to be, since we have 1 kilomole, is just 0.06 divided by 1, right? Let's be clear about that. So it's going to be 0.06 meter cube per kilomole. This is also going to be 0.03 meter cube per kilomole. And what do we know? We know R is going to be 8.314. It's a universal gas constant. Joules, kilojoules per kilomole Kelvin. This is known. Joules per mole Kelvin, kilojoules per kilomole Kelvin, both are fine. Now A, so we need to find A. A is going to be 27 by 64 R square TC square divided by PC. Now if we use a table, so from tables, so in a property table you will find the properties of argon. From there you can find TC and TC. TC is going to be 151 Kelvin for argon. PC is going to be 48.6 bar. So what would be A? A is going to be 27 by 64 into R square, which is 8.314 square, into TC 151 square divided by 48.6 into 10 power 5. So let me just quickly find what is A. So 8.314 to 151 divided by 10 power 5. So A is coming around 0.1368, around that. Now let's substitute it here. So what we need to find is we need to find T2, right? So let me rearrange then. T2 is going to be T1 plus 2A by 3R into 1 divided by V2 minus 1 divided by V1. Okay, that is there, which is equal to 400 Kelvin plus 2 into 0.1368 divided by 3 into R is going to be 8.314. Yeah, anyway, and into 1 divided by V2 0.06 minus 1 divided by 0.03. Let's find out this also. So it is going to be into 2 divided by 3 divided by 8.314, 1 divided by 0.06 minus 1 divided by 0.03. Okay. We calculate again minus divided by 0.03. This is in negative, minus 16.67 into 2 into 0.1368 divided by 3 divided by 8.314. So I am getting something around 400, 0.182. Yes, there could be some mistake while substituting this. I think maybe kilojoules per kilomole. Okay, 8.314. Let's stick to SI units, because if not it will become problematic. So kilojoules per mole. Okay, if that is the case, this is fine. And when you substitute here, so it is going to be 0.06 divided by kilomole is going to be 10 power minus 6, sorry, 10 power minus 3 plus 1, 10 power 3 divided by 0.03. Okay. 0.06 divided by 1000, 1 divided by 0.06 minus 1 divided by 0.03. Okay, so it's going to be minus 16.66 divided by 10 divided by divided by 1000, and by 1000 is 10 power minus 3. It's going to be 10 power 3, 10 power minus 3, 1 by 10 power minus 3 into 10 power 3 into 10 power 3 into 2 into 0.1368 divided by 3 divided by 8.314 divided by 10 power 3. Alright, looks like this is the answer. So if that is the case, then minus answer is going to be 0.182, so it's 399.8 kelvins. Okay, so do recheck this calculation once again, and if there are any errors, please let me know. And let's try the same thing with the ideal gas equation of state. Second is to use ideal gas equation of state. Gas equation of state, everything is going to remain same except that the du is going to be, let's write it down, du is cv dt plus, I think it's t times dou p by dou t at constant v minus is it t, yeah, minus p times dv, minus p times dv, which is equal to 0. Now you can look at it. So the dou p by dou t at constant v we can find. How do we find? We know that pv is equal to rt, pv is equal to rt, so p is equal to rt by v, and it is a constant volume. So this is going to be, how much is this going to be? This is going to be r by v. And now this is going to be r by v. Now t times dou p by dou t at constant v minus p is equal to rt by v minus p, which p we already know, p is nothing but rt by v. So it's simple. So this is simply 0. So this part is equal to 0. Now du is equal to cv dt, which is equal to again 0. So dt is simply equal to 0, which means T2 minus T1 is equal to 0, which means T2 is equal to T1. In a way, ideal gas is simpler. So T2 is nothing but 400 Kelvin. Alright, so this is how you use the property relation for any given gas. It no need to be ideal gas or any, it can be even real gas. But this equation is going to be remain same, right? This equation is going to be same this equation, if I say this equation should will be always same for any gas. So we can use this relation for any gas, and you can find the change in internal energy. So that is one of the advantage of these properties. And people also can construct the property tables using these relations, whatever the relations we studied. I think we found that the final temperature of argon in both van der Waals and ideal gas equation of state. So this is done. Do check my answers once again. Do your own calculations because I might do a lot of arithmetic mistakes. Now coming to our second question. A gas has an equation of state PV minus A is equal to RT where A is a constant. Okay, so they gave a equation of state for gas. Explain whether this gas can be cooled by throttling or not. Okay. So whether this can be cooled by throttling or not is what they are asking. Okay. So we know that throttling has to do with Joule-Thomson coefficient. So we will be using that. Let me write the equation of state again. P is V minus A is equal to RT. Right. Now we know this Joule-Thomson coefficient, right? So how does Joule-Thomson coefficient look? Mu j is going to be 1 divided by Cp times, I think there will be T over here, T dou V by dou T at constant P minus V. Okay. So this is the Joule-Thomson coefficient. Now let's find the Joule-Thomson coefficient for this gas. So we already know it is going to obey this PV minus A is equal to RT. Let's use this. So if we use that, dou V by dou T at, is what we need to find. Let's write this in terms of V. So V minus A is equal to RT by P. V is equal to RT by P plus A. Now we know dou V by dou T. How do we find dou V by dou T? At constant P we need to find. So it is going to be just R by P. A is just a constant, right? So let's substitute it back. So once you substitute it back, what happens? 1 divided by Cp times T into R by P, right? R by P minus V. Substitute V also over here. 1 divided by Cp into RT by P minus V, which is RT by P. Yes. So let's write it in common. A. Okay. Now you can simply cancel these two because they subtract each other, and which will be left with, which will be equal to minus A by Cp. So this is the Joule-Thomson coefficient. Okay. Now we know A is constant, so we should we should explain whether it can be cooled or not through throttling. Alright. So to cool, what we should have, whether we should have mu j to be positive or negative, that can be found using this PT graph. So P and T, and we know that there is going to be isenthalpic lines. So it will have something like this, something like this, right? Again something like this. So, and then there will be this inversion points where the slope will change. Pardon my drawing, it's very bad. So this is the inversion curve. right? This is the inversion curve. And what do we know? We know that this is temperature increasing, so we should have dou mu j, no, not dou mu j. So mu j is negative here and mu j is positive here, right? Now, so we know that yeah. So from here, this would be your initial state or any initial arbitrary initial state P1 and T1, and you will be, if when you do throttling, it's going to be an isenthalpic. So let me just write this also. These are H equal to constant lines. H constant lines. So when you go from here to here, let's say, what do you see is temperature decrease. Oh, sorry, I think this should be opposite. This should be temperature and this should be pressure, right? So this is how you go in the isenthalpic lines from here. So when you have a, when mu j is negative, what you see is the temperature increases, and when the mu j is positive, what you see is this part is where temperature decreases from highest to lowest, right? So it all depends on what is mu j. So is mu j positive or negative? So when it is positive, we are going to have a cooling effect. When it is negative, heating effect. So in this case, this boils down to A, because Cp is always positive. Cp is greater than 0. So then it boils down to whether A is positive or A is negative. So now if A is positive, let's say, then this tells that mu j is going to be negative, right? Or you can say mu j is less than 0. Then what do we get? We get, so we won't be able to cool down. So it all depends on the A constant here, whether it is positive or negative in the equation of state, right? And if A is negative, positive quantity, because A minus into minus plus, and mu j is going to be greater than 0, this will create a cooling effect. So ideally speaking, this gas could be cooled, which behaves as P into V minus A by RT. This gas can be cooled only when A is negative. If Na is negative, then we can have a cooling effect. So that is what this means. I think this question. Now let's move on to the third question here. In this third question, what we have is, so this is actually given in uh, Eunice Sengel book of thermodynamics. So they gave in terms of British, units. I actually wrote this equation, wrote this problem in terms of SI units, so you don't need to worry about it. So put a degree over here. All right. So let's look into what the question says. So the question says 0.23 kg of saturated water, saturated vapor, is converted to a saturated liquid by being cooled in a weighted piston cylinder. Right, piston cylinder device. So there is a 0.23 kg of saturated vapor present initially, and all these saturated vapor is getting converted into saturation liquid. Okay, saturated liquid. And how it is done? By placing a weight above it. So when there is a piston and there is a weight, and when it is freely allowed to move, then what we know is, we know the pressure will remain constant. but because of change in phase from liquid vapor to liquid, there's going to be a reduction in volume, right, when you keep the pressure constant. So when, if that is the case, yeah, so that is also given in the question. During the phase conversion, the system volume decreases by 0.04 meter cube. That is fine. And while it is getting converted to a saturated liquid, 260 kilojoules of heat is removed. So 260 kilojoules of heat is removed, which means basically for converting a saturated vapor to a saturated liquid, during this energy is liberated, and that much amount of energy is nothing but 260 kilojoules. So basically what they are trying to say is this 260 kilojoules of heat is nothing but HFC, right? The energy required to, or energy gained when converting saturated vapor to saturated liquid, right? They are telling the temperature remains fixed at minus 9 degrees Celsius. That is known because it's a phase change. Now let's what we are asked to estimate, we are asked to estimate the boiling point temperature of these substances when its pressure is 4 bar. Right? Initially, what we had was 3 bar, and during 3 bar, this much amount of heat is removed, and this much at this temperature, I've been operating this piston cylinder device. Now, what if I change the pressure to 4 bar? What would be my, what would be this temperature? Basically, what would be the boiling temperature? Boiling point temperature of this substance is what they are asking. That is to estimate. It is not the accurate value, right? We are asked to estimate. So remember that. So we will come to this estimate word. Why they say estimate again, right? And then estimate the saturation pressure of a substance when it temperature is minus 6 degrees Celsius. So they are asking, what if I change the temperature to minus 6 degrees Celsius, and if that is the case, or let's say my boiling point temperature is minus 6, what should be my saturation pressure is what they are asking, right? And then finally to estimate SFG. This is SFG, which is nothing but entropy change associated in the phase change process. All right, let's get started with this question. What do we know? We know that saturation pressure initially was right at P1. P1 is nothing but 3.5 bar, and at T1 is nothing but minus 9 degrees Celsius, and this 9 degrees Celsius is nothing but minus 9 plus 273 is 264 Kelvin. Okay, 264 Kelvin. So this saturation pressure and temperature, what we know is, we know some amount of energy is released, which is nothing but HFG, right? So basically we know Q is released, Q is 260 kilojoules, right? From here we need to find HFG. Okay, we will find it, and the system volume decreased by, so let's say vapor, I'm using capital V here because it's a volume, it's not a specific volume. So volume decrease, let's say, then it's nothing but V2 minus V1, or we can write it like VF minus VG, right? VG is going to, sorry, VG is going to be higher. So Vg minus Vf is going to be 0.04 meter cube. Okay. So from this we can find specific volume, right? Vg minus Vf is nothing but Vg minus Vf divided by total mass, right? What is the mass given? Mass is already given. Mass is 0.23 kgs. Okay. So then let's 0.04 divided by 0.23. How much is this coming? 0.04 divided by 0.23 is I'm getting around 0.174 meter cube per kg. So this is known. So total this you can write it as VFG. VFG or VGF, whichever is convenient. 1 meter cube per kg. And what do we know about HFG? HFG is in kilojoules per kg. So it's nothing but this much amount of heat is removed for certain mass, right? So it is going to be 260 divided by 0.23, this much amount. So it's going to be 260 divided by 0.23, 130, 1130.4 kilojoules per kg. All right. So now we have HFG, we have VFG, and we have saturation pressure and temperature. What we can do is we use Clapeyron equation, because we use basically dp by dt, because using that dp by dt, which is nothing but a slope in a PT curve, in a PT graph, right? Uh, if we know the slope, we can use that slope to find the saturation pressure and temperature at different for different pressures. So we will know that. So what we know about Clapeyron equation, it's nothing but dp by dt at saturation is nothing but hfg by t times vfg, right? So now let's put it all together. Hfg we know 1130.4 kilojoules. Let's write in terms of joules per kg, and temperature is 264 Kelvin, right? 264 into 0.174. Okay, how much is this coming out to be? Into 10 power 3 divided by 264 divided by 0.174. So I'm getting something around 24.608 into 10 power 3, probably be in Pascal per Kelvin, right? dp by dt. Okay, let me just rearrange this. Kelvin. All right, now let's try to estimate tsat. Tsat at what we are asked to find first is tsat at p equal to 4 bar. Okay, let's use this dp by dt sat, and if we use that, basically what I'm trying to do is, let me draw in terms of pt graph and I will show you. So this is p and this is t, right? So how would might look something like this. It's a liquid vapor, right? So this something like this. So it's liquid, this is vapor, and so this is triple point or something. Okay, this is how PT graph looks like. So now we found dp by dt sat at a certain temperature. So let's say this is the temperature. So this temperature is what is the temperature? 264 Kelvin. Right? 264 Kelvin, and the corresponding pressure is around 3.5 bar. Now let's say if you increase to 4 bar. That's the question. Let's say if I increase to 4 bar, what is going to be my corresponding tsat? Is what they are asking. So that's why we found this dp by dt sat, because we can draw we know, so using the slope we can find the desaturation. So let's use that. So dp by dt sat. The reason we say estimate is we found the slope at the 264 Kelvin, and we are trying to, and we are telling that from 264 to whatever the tsat are, from 3.5 bar to 4 bar, there's the this vapor line is going to be, this saturation line is going to be almost linear. So that is the reason we use the word estimate. So that is the reason they asked us to estimate. Right? Okay, let's do that. It's going to be, let's say, P2 minus P1 divided by T2 minus T1. So again, this is something you are approximating, and this is going to be equal to 24.608 into 10 power 3 Pascal per second. What we have to find, we have to find T2, right? So T2 minus T1 is equal to T1 divided by 24.608 into 10 power 3. Okay, so P2 minus P1 is nothing but 4 minus 3.5 bar. So since it's a bar, I'm putting a 10 power 5 over here. 24.608 into 10 power 3. And so we need to find T2. T1 is going to be 264 Kelvin. That's what we used, right? Right, 264 Kelvin. So it's going to be 264 plus zero point 0.5 into 10 power 5 divided by 24.608 into 10 power 3. So now let's just quickly find out what is the answer. Zero point 0.5 into 10 power 5 divided by 24.608 divided by 10 power 3. Okay, so I'm getting a 2 Kelvin increase. Add it to here. So it is around 266.03 Kelvin. Okay, so when we increase the pressure, the saturation temperature also increases, right? So that is what it means. Okay, this we estimated it. Now we need to find, now we need to estimate. Even in the second question says that saturation pressure, we need to estimate the saturation pressure when its temperature is minus 6 degrees Celsius. Okay, estimate PSAT when TSAT is minus 6 degrees Celsius. What is minus 6 degrees Celsius? Minus 6 plus 273, 267 Kelvin. All right. We are just since again it is also in the neighborhood of 264, we can use this approximation of constant slope between these ranges, and hence we can write dp by dt sat equal to again p2 minus p1 by t2 minus t1, right, which is equal to 24.608, which we already found, into 10 power 3. Here P2 is what we are going to find out, and T2 is going to be 267 Kelvin, and T1 is going to be 264 Kelvin. Okay, and P1 is going to be 3.5 bar. So let me also write it here to be clear. Here again P1 is 3.5 bar, P2 is 4 bar, P1 is 264 Kelvin, and T2 is going to be T2 is what we need to find out. Okay, so coming back to this question, we need to find P2. P2 is nothing but P2 is equal to P1 plus, I'm just rearranging the equation, is going to be 24.608 into 10 power 3. Alright, so P1 is going to be 3.5 bar plus T2 minus T1, which is 267 minus 264, basically 3 Kelvin, into 24.608 into 10 power 3. Let me just quickly find this also. 267 minus 264, okay, 3 into 24.608 into 10 power 3. Okay, and it's a 3.5 bar, right? So plus 3.5 into 10 power 5. I'm getting something around 3.5 plus 0.7384 So this is going to be around 4.24 bar. Saturation is 267 Kelvin, then we have a pressure increase of 4.24 bar. Okay, so temperature increases, pressure also increases. Or asked in the third question. Third question says estimate the SFG of the substance at minus 9 degrees Celsius. So how do we find SFG? Let me write that down. Estimate SFG at T equal to minus 9 degrees Celsius, which is for the um, experimental case, right? 264 Kelvin. So basically this device is used to find what is the kilojoule. So basically it's kind of an experiment to find out what is HFG. So for this case, what is the total change in entropy we need to find? Entropy we cannot measure, right? So entropy can be found only through these relations. So how do we find HFG? What do we know about phase change processes? We know that for phase change, TH is equal to just TDS. There won't be any additional term, right? It's going to be simply TDS. So if that is the case, then this can be written as H of G is equal to time T times S of G. So this we can use here. S of G is equal to H of G by T. It's a simpler one. There is another way also to do it. We just use the TDS relation currently. There's another way to do it. We'll see that during this what happens. So HFG is we already found HFG. How much is that? 1130.4 kilojoules per kg. 1130.4 kilojoules per kg, right, divided by 264 Kelvin. So it is going to be 1130.4 into 10 power 3 divided by 260 into 4. So coming out to be 4.28 kilojoules per kg Kelvin. This is one way. There is also another way. What from the Clapeyron equation, right? So let me take a look at Clapeyron equation. So if you remember, before we get HFG, we get another form of equation. So this is the Clapeyron equation derivation, right? So in this, what happens during phase change? It's going to be at fixed temperature. So this pressure is also going to be only a function of temperature, right? So this part goes to 0. So dH is TDS. That is what we use now. So R SFG is equal to SGF by T. That is what we use now, right? So but what we also know is we know from the Maxwell relation, dou S by dou V T is equal to dP dt sat or dP by dt at constant volume, right? So we can use that relation. Okay, let me try that relation also. So from Maxwell relation, dou S by dou V, right? Dou S by dou V at constant T, and this is phase change, so it's going to be at constant T is equal to dou P by dou T at constant V, dou P by dou T at constant V, which we can write it as dP by dt saturation, right? For this phase change process, we can write it as dP by dt saturation, right? So now let's we can write this d dou S is going to be S of G, right? This G minus S of, which is nothing but S of G, is equal to dP by dt sat times delta V, right? So this actually goes here. It's nothing but VFG. Let's multiply these two things. So dP by dt sat we already know 24.608 into 10 power 3. 24.608 into 10 power 3 into VFG. VFG is 0.174 meter cube per kg. 0.174. Let's multiply these two. 24.608 and 0.174. So 4.28 again, same thing. So equal to 4.28 kilojoules per kg Kelvin. Okay, there are two ways of doing this. This is an alternative. One is through a simple TDS equation. One we can use the Maxwell relation. Okay. So basically from here only, if we substitute SFG to be HFG by T, then we get Clapeyron equation. You can go backside also. All right. So and I think this is also done. HFG. So this is how you find the uh, boiling temperature, pressure, and SFG for a given phase change system. And this is the third equation. Okay. Then we also looked at second. Yeah. Yeah. So yeah. So that's it. That's all. We solved three problems today. Let me just quickly revise. In first question, we need to find final temperature of argon during this free expansion, right? When you remove the fission during this free expansion, what is the temperature change we were asked to find? And how do we do it? We applied the first law, and then we use the internal energy equation of the internal energy change, which is equal to 0, and using that equation we were able to develop a relation to find the temperature. And we know that argon can either behave as van der Waals equation of state or ideal gas equation of state. So that is what is given in the question. So if it behaves as a van der Waals equation of state, what is the change in temperature? And if it behaves as an ideal gas equation of state, what is the change in temperature is what we were trying to find. And what we use it, we need to find out whether CV is a function of temperature only, or CV is a function of both temperature and specific volume. We need to find that. So to find this, what we did is we used this relation, and we tried to apply the exactness condition, because that is the total change in entropy is an exact equation, right? So when we applied it, it turns out that CV could be function of only temperature. It cannot be function of volume. So that is clear for the van der Waals equation state. Um, what we also used is we also used another information about argon. Argon is a monatomic gas. So for argon, CV is going to be 3 by 2R, which is a constant. So we took CV to be equal to 3 by R. So CV can either be a function of temperature, but in this case, argon is for CV is just a constant. So that is not a problem. So now, since CV is a constant, it basically simplifies our integration. And once this integration is done, we substituted all the values, and we were able to get the temperature change. So for when we use van der Waals equation of state, we get a very small reduction in temperature, 398.8 Kelvin. And when we use ideal gas equation of state, it turns out that temperature doesn't change during this free expansion. So T2 and T1 is same, 400 Kelvin. Okay. That is the use of this property relations we develop. And the next is whether a gas can undergo throttling or not. For that, it's simple. We need to just find the equation form for Joule-Thomson coefficient. And once we find the equation form for Joule-Thomson coefficient, we can easily say, based on the sign of the Joule-Thomson coefficient, we can say whether it can be heated or it can be cooled. So basically, that's what we did here. And the third question is about using the fact that um, during the conversion the heat is released, and that heat is nothing but HFG, and during using the Clapeyron equation we were able to find the slope in the PT graph, right? And since we can find slope during at that temperature and pressure, we can apply that slope to a nearby temperature and pressure and to find the other saturation pressures and temperature, right? So when we have this, we found this uh, dp by dt saturation for this temperature using the experiment what we call the weighted piston cylinder device. Using this device experiment which calculates how much heat is removed from this device, using that we were able to using that if we apply the Clapeyron equation, we were able to find dp by dt sat, which is nothing but the slope in the PT loop. And now let's say in that neighborhood of 3.5 bar and 264 Kelvin, if we want to find other saturation properties, we can do so by this knowledge of dp by dt sat. So what we try to do is, we let's say if I have 4 bar, let's say zero point 0.5 increase in bar, then what would be my saturation temperature? We use the same slope to find the saturation temperature. So this is just an estimate. My saturation temperature would increase by 2 Kelvin also, 2 Kelvin, right? And it's an estimate, so it's going to increase by 2 Kelvin. Similarly, when we have increase in temperature, what is the increase in pressure we are getting? So that is going to be around zero point 0.7 bar also. So using the same slope, using the same knowledge of same information about the slope. Find is, we also found entropy change which cannot be found or physically measured in the using experiments, right, in this piston cylinder arrangement or in this piston cylinder device. So we found that using this relation, using that information about phase change, which is Th equal to Tds. It can also be found using Maxwell relation, and we know that the H2 is going to be same. Okay, so I hope this would be helpful. All these problems would be helpful to solve your assignment. And if you have any doubts or if you have any problem you find while solving this, you're free to contact me, or you're free to post your questions in the discussion forum, and I will be able to respond it. Or you can come next week and we can have a chat about it. And if you have any questions about the previous, if you have any questions about the classes, if you have any questions about the assignment problems or the interaction session problems, you are free to contact. Okay. All right. This I will stop this session this week. Thank you.